Okay, let's talk about integration by parts. Now, here's the theorem for integration by parts. It says if u of x and v of x have continuous derivatives, so we have two functions of x with continuous derivatives, then the integral of u times the differential of v is equal to u times v minus the integral of v times the differential of u. The way that you want to do this is you want to set this up in a way that your choice of u and the differential of v leads to a simpler integral on the other side. So let's take a look at an example. Let's rewrite this up here. Integral of u dv equals u of v minus the integral of v du. Alright, so let's look at this integral here. Let's say 3x times e to the x dx. Alright, in this case, I have a function that's relatively simple to integrate in e to the x. Integrating and taking the derivative of that is relatively easy. And I also have a function here that's algebraic. If I take the derivative of this function, 3x, I will end up with a much simpler function, a constant function. This is a linear function, 3x. If I take its derivative, I get a constant function. So that is actually what I'm going to make my choice of u and v from. The fact that this is easy to integrate, and when I take the derivative here, it becomes simpler. So what I'm going to do is I'm going to let u equal 3x and dv I'm going to let be e to the x dx. E to the x dx, the differential of v with respect to x. So I have this thing can then be transformed this way, because if you notice, this is the integral of exactly what I'm calling u, 3x, times exactly what I'm calling dv, e to the x dx. So I can do this substitution as the integral of u dv. And that's good because I have here in the integration by parts theorem a formula for integrating u dv, which is exactly what I'm doing right now. I'm integrating u dv. It says I have to multiply u times v. Well, I don't know what v is. I have dv, and I have to subtract that from the integral of v times the differential of u. Well, I can find the differential of u here. First, I take the derivative of u with respect to x. So I'm going to take the derivative of u with respect to x. That's du dx is equal to 3x, in which case I see that du is equal to 3x dx. Also, I can do the same thing for v. I can integrate both sides here, and if you integrate dv, if you integrate here both sides, if you integrate dv, you get that v is equal to, and the integral of e to the x dx is e to the x. So we have this, and we can actually go ahead and find the integral. This formula says that the integral of u dv, is equal to uv minus the integral of v times du. V is that times du, and du is this guy, du. So that's how this integral is going to wind up looking. So let's go ahead and plug everything back in. That means that this is equal to u, which is 3x, times v, which is e to the x, minus the integral the integral of v is e to the x once again, times du. Well, du actually is not 3x dx. Du is actually 3 dx, not 3x dx. It's just 3 dx. There's correction there. So du is equal to 3 dx. 3 dx. And this is not that hard of an integral to do. Let's see. We have 3e to the x. You can pull that 3 out, minus 3 times the integral of e to the x dx, which I've already done. The integral of e to the x dx is e to the x. So this is equal to 3 times 3x. Sorry about that. U is actually 3x, not just 3. U is actually 3x. So we get uv, which is u 3x times v, which is e to the x. 3x times e to the x minus the integral of v du. V is e to the x and du is 3x dx. So now this is correct. That was not correct before. And this should be 3x here, 3x. So this is going to equal 3x e to the x. And then here we have minus 3 e to the x. So this is the final answer for that. All right, let's take a look at another example. All right, so another example would be like the integral of x squared times the natural log of x dx. All right, so we have x squared and the natural log of x. What we need to do, we're going to employ this theorem. The integral of u dv is equal to uv minus the integral of v du. That's what we want to do. So we need to make our choice of u and v and find their derivatives. So u is usually the one that we want to get simpler when we take its derivative. X squared would get simpler, but the natural log gets really simpler. It changes from a transcendental function to an algebraic function. So that's actually what I'm going to make my choice of u this time. And dv, I'm going to let dv be the other function, which is actually x squared. And that would be x squared dx. So now I am going to go ahead and I am going to find all the other parts I need for this theorem. Well, the other parts that I need to find the derivative of this, or the differential, and I need to find the integral of that, v. So du dx will equal 1 over x. So it turns out that du is equal to 1 over x dx. So there I have my du. And v, well, in order to find v, I integrate this. Integrating dv gives me v, and integrating x squared, I get 1/3 x cubed. So there I have all the parts I need. So this is equal to, well, it's going to be u times v. U is ln of x times v, which is 1/3 x cubed. So that's 1/3 x cubed. So that's uv minus the integral of v, which is 1/3 x cubed, times du, and du is 1 over x dx. 1 over x dx. So this turns into, well, I have here the x cubed ln of x over 3 x ln of x. And and then this is minus 1/3 of x, the integral of x squared dx. So I get x cubed ln of x over 3, and then this is going to be minus, well, when you integrate x squared dx, we've done that already, you get 1/3 x cubed, which is multiplied by this 1/3 to give me 1/9 x cubed. And there we have, this is the solution. And notice we had a different choice of u and dv in this case.